Now we start again, and we are pleased to introduce Professor Max Souza in his work, which is joint with Fabio Chalub. Max Souza is from the Universidade Federal Fluminense do Brasil, and he will talk about fixation, the fingerprint of evolutionary processes. So thank you.
Thank you. Thank you very much, Chiara. So, yeah, I will talk about work, joint work with Fabio. So we've been doing this evolutionary stuff for quite a long time now. But to some extent, what I've been talking about is it'll be perhaps mathematically simpler. We can think about as linear algebra of evolution for most of the time. Not all the time, but most of the time it'll be linear algebra of evolution. And so what's the framework? Fabio has introduced it a bit already. So I'll be thinking about Markov chains. So essentially determined by Mij, with Mij for me would be the probability of transitate of state I to state j of the chain. That's the dual representation of Fabio. And my Mij will be allowed to depend on, well, I and j, of course, and which is the size of the population, and on a vector p that will be in Rn plus 1. This vector p, well, to be actually in Rn plus 1, but actually not to 1n plus 1, so either each pj is between 0 and 1, and you can think of the probability of type A being selected for reproduction when the chain is state j. And that was termed by us at some point type selection probability, so TSPs, and now this P I will always refer to them as TSPs. So if you weaken a bit the interpretation you do about P, you can think also about all the different processes that include restricted sampling, like the pairwise comparison process. And so this is quite a general framework. And OK, so our two favorite processes, and they fit in this framework, is the Moran and the Wright-Fisher process. Yes, Moran is given by Mij as exactly that, and Mij, and for me, Wright-Fisher is given by this expression. Fabio has already mentioned, explained quite entertaining what these processes are. You only notice that in all my formulas, our IAJs are switched. So for me, for Fabio, his matrices were column stochastic. For me, they will be row stochastics. So probably people will be happier with that. And if you're a linear algebra person, you'll be happier with Fabio's notation, basically. So OK. Just before going to what I really want to talk, I wanted to make an aside. If you take phi and A equal phi b here, so you can cancel everything out. So this is just capital N in the denominator, and I denominator, so pi equals I over n. And this is usually the so-called neutral type selection probability. So that means that your process has no selection in between. And if you look in a lot of processes, in a lot of literature, particularly the one by Novak and co-authors, the type selection probability intrinsically is chosen this way, and with some functions phi I and phi b, which are the fitness, the reproduction fitness for type A and type B. And usually this reproductive fitness comes from some game theory payoff, but for the purpose of the talk, at least at this moment, it's not so important. And this is essentially taught as a kind of weight average from the fitness you see from the population in frequency types. If you go and define the Darwinian sense, much right as Fisher, as an expected value, conditional what you know on the population today, that's the definition back to Fisher. You can then define the relative Darwinian fitness as, well, psi I of psi b. So psi I is just the expected value, say, of one type. Let's say that X counts blue types, to use the same terminology as Fabio. And so this is the expected frequency the next time, so that's so the ratio of the expected value in the next step for my value today. And this is for type B. And then I can define the Darwinian fetus as this ratio of the two expected values. So if things are really consistent, you would expect that phi would be psi I over psi b should be the same as for phi I over phi b. That's what you'd expect. And turns out, and when that happened, we say that the reproduction fitness is compatible with the Darwinian fitness. And turns out that this happens if and only if that rule here is obeyed. So that so the expectation of, so if you divide everything by n, so that means that the expected frequency at step k plus 1, conditional you know the frequency today, is exactly pi, which is the I entries of type selection probability vector. And that means, if you go back to the original process, that Wright-Fisher is consistent. Wright-Fisher exactly satisfies that, but not the Moran process in general, unless you make further assumptions. And just say an aside to say that why to some extent you will prefer in many places to stick with the Wright-Fisher process, but I mean this is not really not necessarily, particularly if you have weak selections, as Fabio was using in his talk, then again this compatibility is regained up to the correction orders. So okay, so I'm going to introduce one of the favorite classes, what we call the Kimura class. So for Fabio, it will be the transpose of this matrix. And this is essentially, I'll say that the matrix is a Kimura class if it is of this form, with M2 being a substochastic irreducible matrix. So this is a non-zero vectors, and this is the zero vectors in Rn minus 1. And this is the no textbook Markov chain matrix, and you would find in Carlin Taylor, except that's not be in this labeling. I mean, usually this will be bring here as an identity, and you're going to see that later on that this actual formulation is quite convenient for you to do. Now, but in principle, you don't need to do that. And this covers almost everything you can think about of Markov chain process associated with evolutionary process. Diagonal processes that are without mutation, so with two absorbent states, 1, 0, and 0, 0, 1. That goes in Wright-Fisher process, lambda process, and whatever. And for this class of matrix, you can show that there's always a fixation probability vector. That's exactly that. I mean, you can kind of a Highlander motto here. There can be only one at the end. So only one type will remain. And this vector describes exactly that and can be computed straight away from inverting this matrix here, which is always invertible. And you can show actually that the vector f satisfies this condition here. So it's a 0, 1, and in the interior f2, fi is always between 0 and 1, and strictly positive is strictly less than 1. So we always call a fixation vector that is between 0 and 1, with 0 and 1 at ends, and with f, the interior fi satisfying these inequalities and an admissible fixation vector. So that's one way of saying this proposition. Also tells us that Kimura matrices always leads to admissible fixations. So some terminology. We say that the fixation vector f is, well, it's admissible if it satisfies that. Is regular if it's strictly increasing, and is weakly regular if it's non-decreasing. Okay? So question to the audience. What would you expect for a fixation vector to be? So I'm telling you that, so for birth and death process, you go 1 and 1. It should be more or less, almost dying to say it should be increasing. Because if I can only skip you one step at a time, if I'm CEFET, the more than B as a population state, the probability of fixation should be larger than have less than B. Because, I mean, the population has to go to all the states. Okay? And why this question raises, this is basically when you try to do some axiomatic description of this class. And then at some point we're discussing, well, we should have the that. And then I said, yeah, okay. And Fabio said, okay, and fixation is always increasing. And then we always alternated between playing good and bad cop. So I was playing the bad cop this time. And no, we need to prove that, blah, blah, blah. No. I mean, if you don't think reason, there's really no use. Yes? And no, but let's look at what happened. And the first thing that happened is something that essentially confirms that went in Fabio's direction. So if you look at the Moran process, and an admissible fixation, I'll get it right at some point, then F is a fixation of some Moran process if and only if F is regular. So only if and only if F is increasing. So that means that every fixation of a Moran process is increasing. That comes from the formula that you can actually find in textbooks. But more interesting, and George will be happy with that, if you solve the inverse problem, it can always be solved uniquely. So for each fixation, I can give you one and only one Moran process that will give this fixation. So that's interesting because you see fixation is really describe the very asymptotic behavior of the process. But for the Moran class process, if you give me how it fixates, I'll give you what the process is. I mean, the whole dynamic somehow is tied to that. And the formula is very simple.
Quick question, Max. Is it continuous? Is the inverse continuous?
I mean, it continues in what sense?
Well, stable. I mean, you said that there is a unique solution.
It's stable. I mean,
Stable?
yes. Because it's given for this formula here.
Well, the condition number may be high. I don't know.
No. There's no. I mean, F is given, so there's no connection. It's really like solving a diagonal system in this sense. It's very. And the first time we found that, we said, okay, let's look at the literature. I know somebody has found that formula, but it turns out that no one has found it. So, okay, we're happy with that. And that is, and that's so unique. Okay, so fixation of the Moran process is exactly what you expect. I mean, if I put blues and red shirts in here and have more blues are happier. Blues will fixate more with a higher probability than the red ones. Now, Wright-Fisher process, on the other hand, well, they're more flexible. And they're more flexible exactly in this way. Now, give me any fixation probability that is admissible. So I'm only asking that there's no zero known ones in the interior. Yes? So there's one Wright-Fisher process that will have this vector F as its fixation probability. So Wright-Fisher processes are quite universal in the sense that it can realize any admissible vector. Or more generally, if you start with any Kimura process, you give me a fixation vector, there's always a Wright-Fisher process that will have this F as a fixation vector. And if F is increasing, F is regular, then the Wright-Fisher process that does that is unique. Okay? So, when you find this result, then it's okay. So for Moran process, fixation is always increasing. So Wright-Fisher process, that's not always true. So the question is, okay, can we understand what's going on here? And so we term the process regular or weakly regular. This depending on the fixation vector is regular or weakly regular. And the question is how to identify a regular or weakly regular process. Can I look at I can always compute the fixation, of course. But I would like to look at the process and say, okay, I would like to characterize a regular and weakly regular process. So as I say, for Kimura Birth-Death processes, you have this fixation formula. This is the textbook formula. And this product is never zero, so you can always sum some non-zero terms, so the fixation is always increasing. And so KBD processes are always regular. I mean, not only the Moran process. I mean, any birth-death process will be regular. But I'm still using the explicit representation of F. I need to know, I won't claim I know F, but I have a representation formula for F. Okay, so it depends on that. So in order to say more about that, I'll have to introduce two concepts, vector stochastic ordering and order matrix. I will say that two probability vectors on the simplex are stochastically ordered, and I write that. If the sums are, if the tails of one as weakly dominated the other, and if they strictly dominated, I will say they strictly ordered. So if the tails of U of the vector U dominate all the tails of the vector V, so if this is non-strict, I would say that they are stochastic ordered. If the domination is strict, I would say they are strictly stochastically ordered. And for matrices, I look from the, since I'm using a column stochastic matrix, row stochastic matrices, you just look at matrices coming from the top, and I'll say that a matrix is ordered if the matrix with, when I is greater than J, then the column A dominates the row A dominates the row J. So that's the vectors are ordered this way. And that's why, and that's why that particular representation I chose for Kimura matrices are important. And again, if the domination is non-strict, you say it's ordered. If it's strictly, I will say it's strictly ordered. And last thing, last definition, I would say that a matrix is eventually stochastically ordered or strictly stochastically ordered, depending on the case. If after there's a K-naught, a natural K-naught, such that AK is strictly stochastically ordered, or stochastically ordered for all K greater than or equal to K-naught. So you can have a matrix that's not ordered, but then you look at powers of it, and eventually sometimes it gets itself organized and then gets the either strictly ordered or either stochastically ordered or strictly stochastically ordered. So, proposition that's not hard to prove. If M is eventually stochastically ordered, then M is weakly regular. So that's not hard to prove, and actually kind of know. I mean, in some implicitly. So essentially, so the question naturally is, if you have a matrix that is essentially stochastically ordered, I mean, this is sufficient to guarantee the process is weakly regular. But then you can ask the converse question: is it sufficient? Is it also necessary? Sorry. And that's also came out because of a kind of a comment of one of the reviewers of the paper. A bit, yeah, okay, you know, everybody knows that, so you put a bit more of assumption and you prove more. Fine. So I got a bit upset with that. And then he constructed this counterexample. So this matrix M has a weakly regular fixation, 0, half, half, and 1. And then you can compute by just by finite induction that the form of M kappa. And you can check that alpha kappa minus beta kappa is always greater than naught. And basically this tells you that this M kappa cannot be stochastically ordered for any kappa. So M kappa, I mean, so M is not a matrix that eventually stochastically ordered, but still is weakly regular. So eventually stochastically ordering is sufficient, but not strictly necessary. I mean, you can have different characterizations. But however, if you really want things to be regular, then the characterization of eventually strictly stochastic order is equivalent. So then you have this very nice theorem that is say that M is regular if and only if this matrix is eventually strictly stochastically ordering. And one thing I should mention is that the proof of that is related to look at the matrix. So there will be some nice matrix T that I'm not going to really tell you about that brings you in your matrix to this form, matrix L. And it turns out that the condition of being eventually stochastically ordered for M is equivalent of L to be in this very nice set called PFN. So PFN is a set that I'm not sure if you have heard about that. So we all know Frobenius theorem. Okay, so Frobenius theorem is for non-negative matrix. So PFN is the set of matrix who satisfy the conclusions of the Frobenius theorem. Essentially, there's a single dominant eigenvalue, which is the spectral radius, and the right and left eigenvectors are strictly positive, and in this vector, and as I said already, the dominant eigenvalue is unique. So, and PFN is a very weird set of matrices. It includes matrices that can be negative. So the most common example is the Matless matrices, and it's not even convex. But it turns out that one characterization of PFN is done by Johnson and Tarazaga. L is in PFN, if and only if LK is positive, entry-wise, I mean. So from K is greater than some K naught. So this is K naught. Sure that this is true. And because of that, you can actually show that M is a matrix is regular if and only if it is eventually strictly ordered. So this is a complete characterization. And that's quite interesting because you can now look at the WF process. We know Moran processes are regular, and you know that there exists no regular WF process, but with all the information, you can think that the Wright-Fisher process is regular under these three equivalent conditions. M is regular, the matrix M is strictly stochastically ordered, so look, there is no eventually. So the matrix itself of the Wright-Fisher process has to be stochastically ordered, and that's the interesting thing, this is equivalent to the vector P being increasing. So recalling the reproductive fitness, it was defined by that. So there's a result that known in some extent, I think, but at the proposition the fitness functions are positive and affine, then the type selection probability vector P is increasing. So that means that if you do two-player games, you only is going to see regular fixation. And that's one of the reasons why, for a long, long time, people has only seen regular fixation, because they are usually two-player games. And this is an example of a three-player game that's not regular. I mean, unfortunately, I lost the picture of the fixation graph. So you have to picture in your mind. And the interesting bit about that is that, I mean, if you really look at the relative fitness, this is really, I mean, satisfies with greater than 1 for x near 0, less than 1 for x near 1. So it's really associated to coexistence games. So it's not that I'm doing something very fancy here. Okay. So, but as much as Fabio was telling about, I mean, sometimes, finite populations go on one hand, infinite populations go in another direction. And what you can say about large populations? Well, suppose that you know that a fixation is described by a sufficient smooth function. So Fi is just phi over n, and is increasing. And n is large. And let's take P to take the corresponding TSP for the Moran Wright-Fisher process. Then you can show that this difference is 1 over n. Or basically means that if a fixation is kind of continuous in the sense, then you have to be in the weak selection limit regime. So I'm now interested in large n, and Sherlock Holmes has a quite good quote on that. And Reid is a Scottish philosopher, and he's good on the subject, St. Holmes. He remarks that while the individual man is an insoluble puzzle, in the aggregate he becomes a mathematical certainty. And I'll try to tell as much as I can about this mathematical certainty, a large N. Looking at the Moran process, which is really much easier to do in this case. And why it's much easier to do is because, I'm missing a slide here. So remember that I have this formula for Birth-Death process for the fixation. So I want you to keep in mind that formula for a moment. I think I will appear later on. No. So essentially, we define this theta n of I over n as, well, logarithmic the ratio here. And assume, if I will assume that theta, this should be capital N, that theta n as seen as a function of 0 to 1, just divide everything by n, so this is 1 minus x over x. Yes, and the p I can give it by a C1 function. And just write chi n to the L infinity norm of theta n, and assume there's some theta function with this, all this regularity here. And also let kappa minus 1 equals that. So let's suppose that epsilon n goes to 0, so that guys is converting to that. Psi n goes to 0, chi n goes to 0, and kappa n minus 1 times epsilon n, and this is also going to 0. If you assume all that, you can write f of s equals the minus integral of theta r dr. That's what's called the fitness potential. And then you can write this continuous approximation for the fixation. And you have exactly this error bound. So theta n for phi, capital N is the original fixation for the Moran process. It's just a continuous approximation plus some error bounds given here. And you can actually, even if you assume a bit more about the functions, I can give you a relative bound, a stronger bound than that. But for what you're going to do, I think this is sufficient. So I want you to have n large, but finite and fixed. So and then I write kappa equals kappa capital N, and phi kappa equals phi n. So the difference between what I'm doing here and what Fabio did in the previous talk is that Fabio actually passed the limit to n goes to infinity. So here, I want to think that n is very large, but finite. So that's a difference. I'm not really trying to pass the limits. I'm only trying to find a continuous approximation. So let's now assume that this, so remember that I said that kappa capital N is that, kappa minus 1 is that, and theta minus infinity. So let's assume that this kappa N is actually, kappa minus 1 is large. So that means kappa N is small. Kappa is small. So if kappa is small, that's, and this is what's called the driven fixation, selection-driven fixation asymptotics. The dominance by A case, which is the case Fabio has commented about, it means that A is always favored, can be described by this exponential here, and dominance by B can be described by this exponential here. So this is exponential approximations for the fixation that were known to Kimura, so to some extent these are not new, except the fact that this formulae is valid in a regime which goes longer than or wider than the regime by covered by Kimura's approximations to some extent. And this is because I didn't give you the proof of the theorem, but it's always based on numerical analysis estimates. So this is all have to do with going back to the original formula and reinterpreting it as trapezoidal rules integrations. And then you can use the error estimates and compute everything. So that's how that theorem was proved. Now, that's the nice thing. That's the really nice thing. If you have the coexistence, which is one of the cases that Chiara was studying as well, and then you can write the fixation as a convex combination of two dominances. And that has implications. So remember that Fabio put a a picture that was a Kimura quote saying, well, there will be only one will be remain, and then just beside a quote of Martin Smith, well, in the long run we are all dead. Yes, and sorry. Minor Keynes, and yes, and in the long run we are all dead. So this is to say, I mean, when we have coexistence, typically, if you talk to probabilistic people, they say, well, you know, this is a metastable state. If you look at the chain, you'll be a long time around that metastable state. So although you fixate at the very end is very long. And I mean, what is really relevant is what you see in the metastable state. So the question is that really true? So not discuss as much as the time to fixate, but what happened with the fixation. And just before doing that, we also have the formula for the coordination asymptotics, which I give by just this ratio of truncated normals. And if you're far from the boundary, then you have this normal. And I think this formula 5 is really an improvement. And formula 6, I think it's well kind of known in the literature. So this has already an interesting result that if you are in the coexistence case, your fixation probability at the equilibrium point, no matter what it is, I mean, as far from the boundary, is a half. So that means that your normal distribution, when it's truncated, far from half from the middle of the interval, is really being skewed to one side or to the other side. But let me talk about the near one-half law, and I skip that picture and go to that picture. So this is the location. So thinking about coexistence, and X star is being the coexistent equilibrium. So if the equilibrium is at a half, you get this very nice plateau, which is a half, by the way. And then, so if you talk to people that do evolutionary dynamics, sometimes they will come with this shower argument. Oh, you know, I mean, when you're looking at the fixation of this process, but when you're close to X star, then evolutionary forces are null, so there should be neutral forces. But if you're only neutral, then the expectation probability fixation should be equal to the frequency. So that means that if you are at X star is some value, you should expect the plateau to be at that value. And what you see, that's not quite the case. So this is 0.5. As soon as you rise to X star equals 0.6, this is 1. So this is a dominant fixation by dominance of type A. And of course, and when you go to the other round, 0.59, 0.5, 0.4, this is go to 0. And you can then compute phi n of X star for different X stars, and you can see that it comes 0 all the way. It rises quite quickly, and then it moves. And that's a layer, what you call the coexistence layer. It's thinner as large as is n. So it's essentially proportional to 1 over n. So as n is bigger, this is very, very, means that the change happens very, very fast. I still have time to talk a bit about the two interior equilibrium case. This is going up one step of complexity. Instead of, we still have two strategies, but then we have three-player games at least. So in this case, you can have two equilibria in the interior. So there's either x1 or x2. Just one to be stable, the other be unstable, typically, unless under certain situations. And if you call that case case 1, case 2. This is from the point of view of replicator dynamics. So in the first case, you can have then a convex combination between domination by B and coordination. And in the case 2, you have again a convex combination of domination by A and again coordination. And that's interesting because you can show that depends on how you choose, you can have what we call blocking or tunneling. So blocking basically means that this guy here should be, this should be a bad case, but turns out that it can tunnel the unstable case and stop it that way. And this should be a good case. And, sorry, the other way around. So this should be a good case, but sometimes what happens can be blocked, and so you don't actually manage to get to the other side. And this should be a bad case, but sometimes it can skip that, that unstable case and fixate at one. So that's very different from what you see from the continuous dynamics. Yes, here, for the continuous dynamics, this is a better case than that, definitely. And there will be cases when you have large populations but finite, that it should be the other way around. So for the complete story, you can see these two papers, fixation large in population dynamics and continuous view on discrete problem. So this is a paper that came out last year, and this one, which has been not only accepted, not has published it. And there's something I haven't talked about, which is we can do a bit more than that. We can not only solve the inverse problem for P, that's something that I've mentioned here, but you can also, given a fixation, found the TSP, and then give you a D-player game. So really solving the full inverse problem from fixations to game theory. This has been submitted somewhere. Sometime it will be uploaded to archive, I hope. And the take-home message here, since I'm going to approach the end of the talk, is large populations, they are sometimes behave very much like infinite populations, but they are not infinite populations. There will be very issues that will be different. So large population limit is a singular limit. So just be aware that not everything that you prove or that you expect to see in the infinite population case actually is approached continuously from finite populations. This Linear 1.5 law is clearly an example. Yes, in the tunneling backward I was talking about the three-player game, which two inner equilibria is another example of how things might be very different. And thank you very much for listening.